Good evening, ladies and gentlemen. I'm Amit Sharma from Informa Markets, and I welcome you to RE Master Talk, a webinar series from the presenters of REI, powered by Vikram Solar Limited and Dupont. Today, we connect on live webinar on Bifacial Module Technology with transparent backsheet. Sunbeams do not always come from one direction. Wouldn't it be great if the solar panels could capture these diffuse beams and result in high power density, satisfying the solar power needs? Bifacial module technology is one of the key ways to further improve the annual yield of a PV system. This technology harvests energy from the ground-facing side as well, resulting in substantially increasing the power density. And while talking about bifacial project economics, like any emerging commercialized technology, the global solar industry is just beginning to grapple with how to value the project impact of this technology. Design optimization should be thoroughly evaluated for a project with bifacial solar panels with respect to determining the cost of energy in financial models. Studies reveal the gain in typical project energy production with bifacial panel is up to 15%. Here from the eminent panel focusing on the advantages of Vikram Solar bifacial module powered Dupont Transparent Backsheet technology, clear Tedlar film for more reliability and performance and risk mitigation during project execution and better ROI. Today's webinar will have presentations by the representatives of Vikram Solar Limited and Dupont Photovoltaic Advanced Materials, followed by question and answers. Let me give you a little brief about the participating organizations. Vikram Solar Limited. Vikram Solar is a globally recognized leading solar energy solutions provider, specializing in high efficiency PV module manufacturing of 1.2 gigawatt and comprehensive EPC solutions, having a portfolio of more than 1.3 gigawatt capacity of projects, carrying forward the rich legacy and extensive manufacturing experience of the Vikram Group. Vikram Solar, since 2006, is building on a more than 4-decade-old story. It is the first company to gain recognition as a Tier 1 module manufacturing company in India by BNEF. Vikram Solar products are PVEL and Black and White certified. Out of only 3 Tier 1 companies worldwide, Vikram Solar has claimed SolarRIP certification. Vikram Solar is the only module manufacturer in India to have dedicated half-cut lines and have a dedicated production line with both side lamination. Dupont Photovoltaic. Dupont Photovoltaic and Advanced Materials represents a portfolio of product solutions with over 40-plus years of service to the solar, aerospace, automotive industries, and many others. These products deliver proven power and lasting value for the fast-growing photovoltaic sector, including Dupont Solmet, metallization paste, Dupont Tedlar films, as well as Dupont Photosun Solar Silicon. Please allow me to introduce you to our expert panel. Mr. Ivan Saha, BU Head, Manufacturing and CTO, Vikram Solar Limited. Mr. Ivan Saha is the postgraduate engineer from the Indian Institute of Technology, Kanpur. He is currently heading the technology team of Vikram Solar and is responsible for research, innovation, and new product development. He brings with him over 24 years of industry experience, wherein he has held several positions of leadership in Indian Space Research Organization and Mozambique. Mr. Saha has a vast experience in technology development, large-scale manufacturing, innovation, and process engineering, along with R&D in semiconductors and PV modules. A certified Six Sigma Black Belt, he has published over 60 technical papers and holds several international patents in photovoltaic technology. Dr. Kaushik Roy Chaudhary, Global Technical Leader, Photovoltaic Reliability Program, Dupont. Dr. Kaushik currently leads Dupont's Global PV Field Reliability Program, working on reliability and durability of PV packaging materials, degradation of polymeric materials in field-deployed PV modules, and PV system economics. At Dupont, he has previously led programs on metallization paste for silicon photovoltaics, novel inorganic and hybrid thin solar absorbers, and light-emitting and plasmonic nanomaterials. Dr. Kaushik has a PhD in material physics and has over 15 years of experience in photovoltaic and optoelectronic materials. Ladies and gentlemen, before we proceed with our webinar, I would like to highlight a few important instructions in brief. The audience can feel free to click on any of the widgets available at the bottom of their screens. To know the corresponding information that particular widget is carrying, you can click the Bio tab to learn more about our speakers. You can also click on the Abstract tab to know about today's webinar presentation in brief. Please feel free to ask any questions anytime during the course of the webinar pertaining to the topic by clicking on the Q&A tab at the bottom of our screen. We also encourage you to participate in our question and answer sessions post the presentations, along with the poll questions which would be coming between the presentations. If you still have any questions related to the program, please feel free to ask a question by clicking onto the Q&A tab at the bottom, and our technical assistant would be pleased to help you. I hope you all have a great time during the webinar. May I request Mr. Ivan Saha to present his presentation. Mr. Saha, please.
Thank you, Amit, and sunny greetings from Vikram Solar to the entire audience. To introduce Vikram Solar is a young PV manufacturer, module manufacturer, based out of India and supplying modules to the entire world. We have about 1.2 gigawatt of capacity of module manufacturing. And as Amit described, we are Tier 1 certified by BNEF and DNVGL top performer status. We have a very strong brand presence in across geography, and also we've been able to bring up new products in a constant stream in line with our motto of lowering LCOE and delivering best-in-class products for the industry. Vikram Solar right now is structured into 3 verticals: module manufacturing, EPC, and operation and maintenance. And in EPC, we have a portfolio of about 1 gigawatt of EPC experience in India. And we have had, in the rooftop segment, about 250 projects across 500 sites. In O&M, we hold a portfolio of about 650 megawatts. If you look at the global footprint of Vikram Solar, we have offices in Europe, US, China, Singapore, and India. We have shipped out almost 3 million modules across the world. That is around 2.1 gigawatt of modules as of last year. The Vikram Solar growth story in the last 13 years that we have been in our inception from 2006 to 2019, it has been quite a tumultuous journey, and we have been able to always be at the top of product development, innovation, and state-of-art manufacturing. Presently, we have a 1.2 gigawatt of module manufacturing line, which delivers best-in-class products for the Indian as well as the global market. We have a current employee strength of about 2,500 people, and we have been audited by Munich Re, Solar IF for insurance-backed warranty. Vikram Solar has also been certified as a top performer in DNV GL PQP 2019. Our modules have been featured as the top performing 2% top performing modules amongst all the globally renowned module manufacturers, including all the tier 1 Chinese. How we are creating news. So recently, for example, Vikram Solar bagged a 300 megawatt project worth about 1,750 crores Indian rupees from NTPC, which is the largest government-owned power producer in the country. We are part of the Fortune Next 500 list, and we have been ranked as the #1 Indian module supplier second year in a row. Second year in a row by Bridge to India. Amongst doing business, apart from doing business, we have been also dealing with the phenomena now which is impacting the entire world, which is COVID-19. So if you see on this slide, there are a few images of us doing a bit for our society, giving back to the society, like organizing food and medicines for the local population near our factory and near our EPC sites. So this has been the ethos or the culture that we are brought up with in Vikram Solar, that we try to give back to the society as much as we get from it. Coming to the module development plan or roadmap of Vikram Solar, and here we are talking about the monocrystalline module only, even though we have two series basically, something which is called Somera, which is monocrystalline, and Eldora, which is polycrystalline. In 2019, we have launched the Somera Duple, which is a half-cut module, touching module power of about 395 to 400 watt, and a Somera Plus, which is exceeding 400 watt, 405 watt. In 2020 Q4, we plan to launch the multi-bus bar Somera Plus module, which is basically going to, this is a bifacial module. In fact, Duple and Somera MBB Plus both are bifacial modules. And the target power of this module would be about 450 watt peak. This module is going to be available in 2020 Q4. Let me take a step back and take you to the technology of bifacial modules and brief you a little bit about what bifacial modules are consist of. So basically at the heart of the bifacial module, and here we are talking about bifacial P-type modules, at the heart of the module is a bifacial P-type cell with P-type crystalline silicon as the base material. and it has got emitter at the front, and this is a PERC material, so aluminum oxide passivated rear surface with silicon nitride top capping layer and aluminum contacts at the bottom and silver contacts at the top. So this basically is a N plus P and P plus kind of bifacial, the two junctions, the emitter junctions, and it reacts or is sensitive to light when it falls from the front surface on the N plus P contact and at the back surface to the P plus contact. And this is the way it can be sensitive to light falling from the front as well as reflected light from the bottom. Bifacial modules, as all of you know, has an ever increasing share, and this is the small graphic at the bottom of this slide shows the increasing share of bifacial modules in the world, in the global PV market, which is projected to go up to almost 50% by 2026. Now, when you talk about bifacial module, there are two aspects to it. First is a bifacial module, whether it is the construction of the bifacial module is, as all of you understand, that it has to have two surfaces. So the light has to be reaching both the front and the back rear junction. So the front junction and the back junction both have to be exposed to light. So both the surfaces have to be transparent to the path of light. So you could either have a glass module. Just a minute. Either you could have a glass module as a structure, or a glass to transparent backsheet module. And over the next few slides, I'm going to explain to you how the two go head to head, because both are competitive products and there are pros and cons of each. Over the next few slides, I'm going to take you through that. Next few slides, I'm going to explain to you the benefits of the transparent backsheet module vis-a-vis the glass, and why did we choose to get into the technology with glass to transparent backsheet module. First consideration is the weight of the module. So glass to glass bifacial modules is 22% heavier than a conventional I'm having some problem with the slide, but anyway. So the glass bifacial module is 22% heavier than a conventional monofacial module, owing to two glass layers, one on the top and one on the bottom. So the need is for lightweight modules. Heavier modules means heavier structures, heavier support systems, and so heavier, pillar and posts to mount these modules on the ground, and additional civil costs. So the idea is to make a lightweight module and not a heavy module, and therefore glass module as compared with a glass backsheet module, the glass module loses out. The bifacial glass transparent backsheet module is weighing about 23 kgs, while a glass module is about 28 kgs. The next point is on LCOE. Okay, so LCOE, once you have higher structure costs, that leads to higher installation costs and an overall increase in LCOE for bifacial module. So the need of the hour is to reduce LCOE and hence need for conventional frame modules. The next point is robustness. So frameless glass modules are more prone to bending and cracking during transportation and installation. And this has been a constant issue with glass frameless modules. Now, with the help of glass backsheet, transparent backsheet module, if you have a framed structure, then the robustness improves by leaps and bounds, and there is higher structural strength. The next point is rear side cleaning. So a bifacial module has an additional sun-facing side, which is the rear side. And since it needs to be transparent to the path of light, it requires regular cleaning. And glass bifacial modules require an additional cleaning step, which is at the rear of the module. Now, therefore, there is a need for a module which doesn't require cleaning at all. So here, bifacial module bifacial glass transparent backsheet module comes in handy because the bifacial transparent backsheet module actually doesn't need cleaning at all because the rear transparent backsheet has a hydrophobic or anti-dust surface, so it can repel the dust and the water from the back. So you really, the rear side of the module doesn't get dirty at all. This leads to excellent anti-staining performance, reduction in O&M costs, and reduction in water usage, which is also very important. One of the most important or most dominating issues of glass bifacial modules have been field failures. And you need to understand this concept a little more clearly because field failures of glass modules, even though they are not reported very frequently in the literature, is significantly higher in China and other places where there's been a substantial installation history of glass modules. So this happens due to the following reason. So in glass module, when you have in the glass module, when you have two glasses on the one at the top, one at the bottom, and when you are trying to laminate them, there is something called a lamination pinching effect that happens at the edge of the module. That leads to some compressive stress buildup and air bubble getting entrapped at the edge of the module. When the module is installed and under severe thermocycling conditions, humidity conditions in the field, these compressive stresses actually gets released and the module shatter. This has been one of the major failure modes of glass modules, and therefore it's a significant reliability risk for these kind of bifacial modules being installed in the field. Hence, there's a need for a field failure proof bifacial module. And that is where the transparent backsheet glass bifacial module comes in place. I'm sorry. So okay. So basically, because of all these parameters like weight, LCOE, robustness, rear side cleaning, etc., and field failure, these parameters, when you bring them head to head, it makes a strong case for glass transparent backsheet modules, even though glass modules are pretty strong performers. So it's more like a, the legendary Avengers head-to-head of Hulk versus just a minute. I think the slides are getting stuck. So it's a classic head-to-head of Thor versus Hulk, and in this case, I think it's the transparent backsheet modules which wins. And I'm not going to tell you whether the transparent backsheet module is Thor or it's Hulk. However, that brings us to the next slide, where we talk about how the product development process in Vikram Solar works, and we start with doing a survey. So when you get fixed on transparent backsheet module as the future product that we are going to rely on, we start by doing product development at Vikram Solar. We start with a survey. We do a benchmarking. We do a supplier roadmap analysis. We do a DFMEA analysis. We carry out internal reliability tests, certification, and make the product collaterals, and finally launch the product. So this is the process that we follow. And while taking you to the other steps that we have to cover during this process, so some of the design consideration and manufacturing considerations of bifacial module. So we talk about 4 important design considerations. First of all is WVTR, which is the water vapor transmission rate of the backsheet, when we choose the backsheet for the bifacial module. We find that this slide this slide shows there is a wide range of backsheet materials that are available in the market, okay, with different values of WVTR. And the slide on the graphic on the right shows the DNVGL data on damp heat results of different backsheet materials. This doesn't include Vikram Solar, but it includes a lot of our competitors' data. And if you see the degradation of power after damp heat, which is attributed to WVTR penetration through this backsheet, there is a wide range of degradation, starting from -5% or less than -5% to well over 15% negative. Sometimes, in the case of one particular manufacturer, it goes up to 20% also. The rear side fails fast, so where the backsheet is. While there are several reasons to explain this, what it shows us, choosing the appropriate backsheet is key to get a good module. Okay. And therefore, the backsheet WVTR choice is very critical. Similarly, there is also one more aspect when you talk about the design considerations of bifacial module, that there are there is something called PID, potential induced degradation of bifacial modules, and the PID impacts the front as well as the rear junction. And there are two different physical processes that are involved. The front junction gets impacted by PID shunting, while the rear junction gets impacted by PID polarization. Now, because of high moisture ingress through the backsheet, the mobile ions of sodium, which are principally responsible for PID, actually can deteriorate the rear faster. And this is what also we see in the graph, which you see on the right-hand side. This is our internal reliability testing data, where the rear side fails. The failure rate of the rear side is higher after 96 hours than the front. So therefore, this rear failure is always something which you need to consider, and WBTR is an important parameter as a result of that. Okay. The next point which we also need to consider while designing a bifacial module or the choice of the backsheet is the transmittance value of the backsheet. So glass actually scores high when you talk about the transmittance. So it has a transmittance of about 95%. While transparent backsheets have different values of transmittance ranging from 70 to 90%. But after damp heat, after humidity ingress through the backsheet, the transmittance value actually reduces. So if you see the graphic on the bottom, we talk about the transmittance values reducing by about anywhere between negligible for the first two to, on the supplier 3, it has reduced by almost 10%, from 80% to about 70%, which means the bifaciality factor for this bifacial module is going to be severely impacted if you don't choose the right backsheet. And we are happy to note that our modules, because of Vikram Solar modules, have in conjunction. So we have evaluated many suppliers, and we have been quite happy with the performance of Dupont material when we use it in our as a backsheet, as a transparent backsheet. And this has been proven by our internal reliability tests, transmission retention tests, etc. We do also a very aggressive pressure cooker test where other backsheets have failed miserably, and Dupont backsheets have qualified actually. So the next slide, the other design consideration that we have to look at is also the cell to module ratio, conversion ratio. So because the material is transparent from the front and the back, so some of the light is going to pass through, and you are not going to capture that light because in between the gaps of the cells, there is about 1.5 mm gap between the cells. The light that goes through those gaps, you're not going to catch them. And therefore, the CTM, cell to module loss, is significantly higher in the case of bifacial modules. Now, there are backsheets, transparent backsheets, to mitigate this issue. There are transparent backsheets which uses a mesh or a reflective mesh layer at the gap between the two between adjacent cells, where it creates an additional reflecting surface over which the light can get reflected and be incident on the cell once again, so that you can recover some of that light that actually was escaping. And therefore, using a mesh backsheet will help you to gain back some of those CTM that you are actually losing. The next slide talks about module temperature, and glass backsheet actually are known to get heated up more because it's pretty impervious to moisture, and glass backsheet, the cell operating temperature, the NOCT values are said to be higher. If you have a transparent backsheet, then it allows more heat to be emitted from the rear side compared to the glass backsheet, glass module. When you talk about the manufacturing considerations, with some of the factors that we need to consider, we use POE, and I talked about POE earlier as an encapsulant. One of the reasons why we use POE is because the POE's volume resistivity is very high, and because of that, it effectively prevents the sodium ion migration and reverse PID. The reverse side PID it can improve or prevent a lot. And however, the disadvantage is the POE has a higher polymerization time as compared to EVA, and therefore the capacity utilization of a manufacturing line, when you talk about glass transparent backsheet lamination, is capacity utilization is considerably lower. So you get for that particular for the same particular line, if you make a glass normal normal module to a transparent glass transparent backsheet module, you will actually realize less number of modules per hour of production. Obviously, because you have two surfaces, there are stringent quality checkpoints which needs to be. So some of the things which were hidden behind because of the white backsheet now needs to be checked, doubly checked, because you have a transparent backsheet at the bottom. So the front and the rear surface inspection, visual inspection, and the criticality of the inspection increases multifold. The addition of POE to some common backsheet materials is low, therefore enhanced process time and quality time is required to actually optimize their values. And Dupont backsheets have an advantage in terms of that as well. And because of this narrow process, lamination process, there is a very narrow process window which is available. And there are minor changes of temperature and pressure can lead to bubble formation. These are some of the manufacturing considerations.
Mr. Saha, sorry to bother you. Just keeping it up on the paucity of time, we would request it.
I know. I'm just one slide away. Okay. The two other things that I need to brief the audience about is the STC measurement of bifacial module is still not an established IEC protocol for that. So right now there is IEC 60904 test protocol, which is right now in place, which talks about the bifaciality factor, and some of the laminators that we are using right now in production are not suited for bifacial modules. However, there are new laminators that are being made for top and which can eliminate the module from the top as well as from the rear side, and therefore those are the things that we are going to talk about maybe in the later days once this IEC standard is in place. Just bringing up the last slide, and in summary, the Somera Duple bifacial transparent backsheet module exhibits additional energy yield from the bifacial technology. It has very high reliability because of the factors that we considered earlier, high power generation, and a high degree of plug and play. So basically, it is exactly compatible to a glass backsheet standard module with the racking structures and the mounting and the racking designs. Therefore, it's very easy to install. Thank you very much for listening to us, and I'll be happy to take questions. I am bringing up the polling slide, the first polling slide, and I'll...
Thank you so much for the presentation, Mr. Saha. Yes. Thank you so much for the presentation, Mr. Saha. A very informative presentation. I would request all our attendees to post their questions based on to the presentation. There's this poll slide in front of you. Please vote for it also. You can poll for it. And I would request now Dr. Kaushik to present his presentation, please. Dr. Kaushik, please. Thank you so much.
Okay, do you want me to take it away? I think that there are a couple more polling questions on this. Yeah.
Yes, we'll do it for you.
Okay.
Yes,
thanks, the organizers, and for the nice introduction, and thank you, Ivan, for the nice background and the discussion around Vikram Solar and the technology and the advantages. In this part of the webinar, I'll specifically focus on the Tedlar clear film-based backsheets and how it contributes towards lowering the total cost of ownership for asset owners. As was mentioned, I work for Dupont, and Dupont has been a big player in PV for 30 plus years. The three flagship products that have been serving the PV industry are a silver metallization paste, Dupont Solar, the Tedlar-based backsheets, one of the examples of which we will be talking today, and a silicon encapsulant, the Photosun, that you see on the right over here. And we always try to balance performance with long field reliability, which together would deliver long years of proven performance in order, in turn, trying to drive to lower LCOE. So if we think of LCOE, there's the cost part, as is shown over here. There's the module cost, the operations maintenance cost, the installation cost, the balance of system cost, and then on the other side there's the performance related stuff, the durability of the modules, the energy yield, the system performance, and obviously the module efficiency. Now the way we try to do it is we try to recast this thing in a slightly different mode where we capture all the different aspects. And then we try to reason out how we could add to the whole equation in order to lower the total cost of ownership. As you see here on the left, I'll take you through these four buckets that we have recast all these elements in an LCOE in terms of proven material reliability, in terms of performance, yielding higher energy, in terms of cost, through lowering the cost of installation, balance of systems, and operations and maintenance. And then something that Ivan also referred to, a more mature manufacturing process involving less capital investment. So taking up the first bucket over here, what do we see in terms of material reliability? One of the things that the Dupont Tedlar product is proud about is its 35 plus years of field proven record. Obviously not in bifacials because bifacials were not there, but the technology of the backsheet and the material is very much similar. I'll come to the different aspects of how material reliability plays into the whole thing. So the first question that you might ask is why do we need long-term field proven record? Although the answer is probably pretty obvious, we always try to point towards field performance as our first metric. What I'm showing here in this chart over here on the right is data from a field program that, like some other institutes, Dupont also drives. This is a program that we have been running for over 10 years now. What is seen over here is that year over year, there has been an increase in the number of module defects over the years. And if we now narrow down to our this part of the discussion of the webinar, we are also seeing a corresponding increase in the backsheet defects, be it polymeric backsheets or glass backsheets, which do not go back much further. Now, this report is actually based on a lot of data globally collected, as you see here, over 3 gigawatts of total power. So this kind of points us to the fact that, you know, all modules are not really created equal. So attention to the bill of materials is very critical, as Ivan pointed out, the rigorous process that Vikram Solar runs through in order to ensure long-term reliability and therefore long-term return on investment of asset owners. Okay, so armed with that information, what do we know about any record of the clear Tedlar-based transparent backsheet in the field? Obviously, as I pointed out, there was not much of bifacial out in the field, and therefore there is not a lot of data. However, I want to point out to this one of these examples from the field. There are several of these where there are some building integrated photovoltaics, and this particular one is in Netherlands, in Amsterdam. And this has been in the field. At the time of its inspection, it was 18 years. Now it's 20 years, and essentially no degradation in the backsheet, no yellowing, delamination, cracking, anything. Gives us a lot of confidence in the field-proven record of the material. So this was the older generation of the transparent backsheet. In 2019, Dupont then launched the new transparent backsheet made on based on the improvements in the clear Tedlar film, which actually won the 2019 PV Magazine Award for one of the best innovations. And as we are seeing here on this cartoon on the right, the innovation in this case in the air side or the outer layer, which is the Tedlar layer, and that in turn protects the core and the inner layer of the backsheet from things like UV, things like abrasion, and obviously also holds up to other stressors in the field. So let's take a look at the properties of this transparent Tedlar film. Obviously, what's required of it? You heard about transparency and how we need transparency across the wavelength ranges. So on the right, I'm showing here how this transparent Tedlar film has a very flat 92 to 94% optical transmission over an entire range of solar wavelengths. It needs to have robust mechanical properties and obviously UV protection for the underlying layers. We'll come to some of these. Just to start out with, these are some of the starting out numbers, and I'll detail on why these are important and what these mean in the next few slides. Once we have the Tedlar film, now obviously the backsheet is, as I pointed out, is made out of this Tedlar film on the outer side, and then a transparent PET core and an inner layer. This is also a fluorinated coated layer. On the right, we are showing how this transparency, the optical properties, holds up after 400 kilowatts hours of UV exposure from a xenon source, which actually simulates the sunlight the best way. So what we see here is the optical transmittance, which was at about 93, 94%, is very straight, flat on, all across these hours. The other interesting thing is, as polymers are exposed to UV, the yellowness in the polymers can go up. In this case, it does go up a little bit. However, compared to any degradation in field performance, this is a very low increase, and it absolutely does not affect the performance in this case. Now, what does it do in the field? Here's an example from a tier 1 module maker. They actually put out bifacial modules with dual glass and bifacial modules with the glass transparent backsheet in the field. And for 30 kilowatt hours of UV exposure, what we see here is the dual glass modules actually incurring more power loss, as you see here, 2.7% versus the 1.33. Why this is the case? If we look at the transmittance of the UV in the UV of the clear backsheet versus the 2mm glass, we see here that beyond 350 nanometers, so shorter than 350 nanometers, is the place where there's a lot of harmful UV that's present in the solar spectrum. And bifacial mod and the clear transparent backsheet actually has a much lower transmission, and this in turn compared to glass, and this in turn can protect the rear side of the module from UV degradation, as well as a degradation of the POE and capsulan that's there on the rear side. So here's an example from the field of actually how this improved protection from UV versus glass can deliver in the field. Next, we are looking at two other very important properties. The first is obviously mechanical properties, right? So you need these polymeric backsheets to hold up their integrity, to be robust mechanically over the course or lifetime of the modules. So on top, what we are showing here is that, and this mechanical property is measured by the retention of the elongation. So because these are polymeric materials, they can stretch, and they can, if they become brittle, they can crack. However, if the elongation is retained, we are confident that this will hold up in the field. What we are seeing here is on the top plot over here, I'm showing elongation after UV exposure for, again, 400 kilowatt hour, which actually corresponds to 30 years of field exposure from the backside. And as you see here, both in the two directions of the module, the MD direction, which is the machine direction of the module, and the TD direction, which is the transverse or the perpendicular direction, the elongation is pretty flat. Similarly, after damp heat of 3,000 hours, there's almost no loss of mechanical properties, in this case, the elongation, as we see here. By the way, the requirements for IEC or some other accelerated tests like the PVEL or DNVGL test is much lower than this 150% or way over 150% that we are getting here. We also look at abrasion losses, and this was mentioned by Ivan. The way we measure it is through an ASTM standard test, which actually is much harsher than any field condition that the modules would see. This is essentially 100 liters of sand and surface cleaning. So what we see here is a Tedlar-based transparent backsheet on the left. We are measuring the light transmittance, and it only loses a fraction of a percent light after the entire test, which is way over the lifetime of the module. And compared to some other competitive materials, it's you can clearly see the difference over here, both in terms of the loss in light transmittance, and on the right here, an equivalent test which shows how much of sand is needed to actually wear out the backsheet, which is significantly more than any other competitive backsheets, and also significantly more than anything that a backsheet would see in actual field deployment. Next, I'd like to show some results on PID, as was also mentioned by Ivan. Bifacial PERC cells, depending on the passivation, the rear side passivation, if it's not optimized properly, can lead to losses in power. Showing here results from full-size commercial solar modules comparing glass and a transparent backsheet. More importantly, I would like to draw your attention to the rear side results, and we see clear differentiation all the way up to 384 hours. Mind you, this is again much more harsh than is required by, again, any IEC or other accelerated tests. So at the 192-hour level, there's a clear difference between glass backsheet and glass in terms of power lost. This again has been repeated by another tier 1 module maker, and in that case, actually, the clear backsheet modules almost lost no power after 192 hours. Okay, so Ivan did mention that all Vikram Solar modules go through the PVEL or DNVGL testing, which we also put a lot of emphasis on. So in this particular PVEL sequence, or DNVGL sequence, they have now introduced a backsheet durability sequence as part of the PQP program. And this clear backsheet has been taken through it, the full sequence, and it's shown here on the left over here, and without any cracking, yellowing, or delamination. So essentially no defects. However, as is pointed out in the block over here on the right, there are several cases of faulty backsheets that have gone through the test and have ended up showing defects, very much like defects that are seen in the field. So that brings us to the next bucket, the energy yield bucket. I'm showing here some results, again, field results. We always try to go back to the field to prove our point from a tier 1 module maker. What you see here are 4 different installations of sand fixed installation, sand tracker, and a different surface, a cement with a fixed one, and a cement with a different type of cells. But in all these different tests, over a period of 6 to 8 months, this was done with multiple modules in an array. We see that the bifacial modules with Tedlar transparent backsheets actually outperforms. This is the amount of energy gain that you get over glass modules in all these installations. The reason that that was kind of alluded by Ivan, we believe, is that the bifacial modules have Tedlar on the back, and Tedlar actually has much better infrared transmission spectrum at wavelengths longer than 3 micron compared to glass, and this helps them to handle the heat dissipation from the PV modules better than glass backsheets. So this work, we are actually right now trying to delve deeper into it to figure this out further. Hopefully, I'll be coming back and showing you more results on this, but this is the main belief right now. Coming to the next bucket, towards lowering the cost of installation, balance of systems, and operations and maintenance. Again, something that was mentioned by Ivan. I'd like to add to it by saying that there's a general trend in the market of going towards larger sized modules. So 400 and 450, 460 watt modules are very common now. And there's a push with different module makers to go to 500 watt modules. With that, the module size and module weights would increase even further. And the difference in the weights of glass transparent backsheets and double glass modules would still contribute to the glass transparent backsheet modules to be very attractive. Again, they are less prone to damage during transportation and handling. There's no extra cost during installation versus simpler monofacial modules, and also that these being lower weight. So we believe that these are better fit for a higher power, and definitely for as the market moves towards bigger size modules. Ivan also mentioned the lower O&M cost and showing some actual results here. This is actually, again, a standard China standard test for soiling resistance. What we see here is a comparison between a transparent Tedlar backsheet module on the left and glass on the other. And before rinse, we see all the soiling over here on the top. And after a rinse, which is part of the standard test, you can clearly see the difference between the transparent backsheet versus solar glass, which is used here. On this chart, again, if water is not used and any of the simple organic solvents are used to clean the modules, the transparent Tedlar, which is shown on the right over here, clearly outperforms any of the other clear backsheet modules or materials in this case, either an FEP or a PET transparent coated. Brings me to my last bucket over here. And just very quickly, as I had mentioned, and again, Ivan being a premier module, representing Vikram Solar, who are a premier module maker, can speak more to this. But we all know that, as we mentioned, bifacial, in this case, clear transparent backsheet module making involves less capital investment versus the glass production lines. No loss in yield rate. This was again hinted at by Ivan. With the POE encapsulant, there's stricter process control that's needed, which can actually result in yield losses. With bifacial modules enabled by transparent backsheets, we believe that EVA can be used at the back because of the lower PID loss, and therefore we can take down this yield loss. And again, faster production speeds would lead to higher capacity. The other thing that I did not point out in detail in my presentation is there's a move towards glass modules coming with thinner and semi-tempered glass, which which actually increases the risk of glass breakage during module lamination and further handling. This again can slow down the production speeds and also can lead to field issues and defects in the field. So when I bring all of this together, we now have filled all these 4 buckets, all the way from material reliability on a long term, higher energy yield with actual field data that's going on now, lower installation and other costs involved, combined with the mature manufacturing. We see a clear path towards lowering the total cost of ownership through adopting this clear, transparent Tedlar-based backsheet technology. With that, I thank you for attending the webinar and listening, and I'll be open to any questions with the other panelists. Thank you. Back to you, Amit.
Thank you so much, Dr. Kaushik. Very educative presentation. I'm sure our attendees would have too many questions to ask you on that. We have a small little poll question which is coming across, and while that comes up, I would also like to thank all our audience for their overwhelming response on posting questions throughout the course of the webinar. I would request all our audience to still keep posting your questions, and we shall take them up now in our question and answer session. We have a quick question to Mr. Saha. Mr. Saha, the first question which has come across to you, to Vikram, is, in this model, Vikram is using POE as encapsulating in place of EVA. How is POE a better choice for module performance and reliability?
Yeah, so this is what I had explained in my slide where I talked about, yeah, can you hear me? Hello? Hello? Hello, can you hear me?
I think we can hear you, Ivan.
Yeah, okay. So this is something that I explained to you in the slide where I showed the PID resistance of bifacial modules. So one of the most important parameters, or these bifacial modules are highly susceptible to PID, both from the front and the back, in case you are using a glass module, and from the front primarily if you are using a glass transparent backsheet module. So having encapsulant which is has a higher volume resistivity prevents the migration of sodium ions through the encapsulant, and that is what prevents degradation, PID degradation. So using POE, which is a higher volume resistivity over EVA, is a must, and that is the reason transparent backsheet or glass bifacial modules must use POE instead of EVA, just because of this higher volume resistivity.
Thank you so much. Thank you so much.
Amit, over to you.
I have a question to Dupont. Yes, I have a question to Dr. Kaushik. Compared to a GG module, how suitable is the transparent backsheet module to be used in desert environment with high UV and sand abrasion?
Yeah, thank you. As I had pointed out in my presentation, these are two important considerations, obviously, because your modules have to withstand the UV of the sun, because you are in a light environment. So first up, we point towards the accelerated testing results, as Ivan also pointed out, and as internally I've shown that our backsheets go through, along with the testing that's done at PWell. So after us taking these through UV doses that would clearly match 30 years of field performance, 400 kilowatt-hour, we see very little degradation coming from UV. They have also, after going through the sequential tests at PWell, which also combine a lot of UV, they don't show any signs of degradation. Combine that with the field result that I showed, we are very confident that these polymeric backsheets will be able to withstand 25 to 30 years or even longer UV in the desert. Coming to the sand abrasion, as I showed there, the loss in transmission after significant amounts of sand abrasion is less than 1% of transmission, and this is, say, after 25 to 30 years of field exposure. So these two things combined, we think, makes the bifacial clear Tedlar backsheet a very solid contender to be deployed in any desert kind of environment.
Thank you so much. Thank you so much, Dr. Kaushik. We have a question, quick question to Vikram. And the question is, the generation from ground-facing side of bifacial modules determines the additional yield. How we can modify the ground albedo for a better generation? Mr. Saha?
Yeah, so there are various ways of doing it. So including, if you're putting this bifacial module on rooftop, you can paint the rooftop white and increase the reflectance from that roof. If you are, putting it on the ground and then have a surface which is more reflective, less of vegetation, I would say, which absorbs sunlight, the albedo increases. If you remove the vegetation and have maybe sand or gravel reflecting the sunlight. Plus, there are various other techniques. Like if you are using this on a tracker, for example, these bifacial modules, then there are angles of mounting the tracker and if it's not a continuous angle changing tracker, so there are specific angles of installation which can give higher albedo. So various approaches from the design engineering side, as well as from tracker side. So there are many answers to the question. It depends on which place you are installing this and what is the geographical condition of that site.
Thank you. Thank you so much. Yes, thank you so much. There's a question which says, and this is by Mr. Kavish Shah, does the glass transparent backsheet module doesn't require backside cleaning? What is the cleaning cycle of a glass module?
So
who do you want to take it?
That?
Yeah. So
Mr. Saha,
maybe
Dr. Kaushik,
go ahead.
Yeah. Okay. Why don't I take it and then Ivan can add to it. There have been studies on the frequency of cleaning that's needed on the rear side of a bifacial module, which is put on trackers, and there are slightly different estimates. As Ivan was pointing out, the local climate, the vegetation, the soiling, all are different from point to point. But in one of the studies done in Chile, in a desert kind of environment where there's a lot of soiling, the study pointed out that on the rear side of a bifacial module, you need anywhere from 8 to 11 times less cleaning than it's needed on the front side. So in comparison to the front side, the rear side needs much less cleaning. On top of that, if you now compound the fact that the clear backsheet, by its hydrophobic nature, is a natural repellent of both soiling and is also easier to clean with less amounts of water compared to solar glass, I think you get a sense that in terms of O&M cleaning, this is almost a minimal cost on the rear side. And just to add to that, I personally have been in fields in Western China, in deserts, where the power loss from the rear side have been minimal, with minimal efforts at cleaning.
Thank you. Thank you, Dr. Kaushik. I hope that answers all the queries of our tenants. There's a question I have for Vikram. In With advancement of technologies in our industry like TOP, Cone, IBC, and AJT, and with larger wafers touching the 500 WP mark, what are your views about the competitiveness of the bifacial module with its counterparts? Mr. Saha?
Okay. So the counterpart, I guess, is the monofacial module. But see, all the technologies that you mentioned, TOPCon, AJT, IBC, all of these technologies are uses bifaciality of the cell as a starting point. So double-side light-sensitive surfaces. And obviously, when you have a double-side light-sensitive cell, you need to have a bifacial module, which can actually transmit light from both sides, and the cells can generate power from both the surfaces. So as a technology, we are moving away significantly, as I was showing in my ITR TV projection curve. In the next, we are seeing something like in the next 4 to 5 years, a complete shift in the technology from monofacial to bifacial. And all of these high efficiency technologies of cell efficiencies going up to 24-25% efficiencies with larger size wafers, M6 and M12 wafers, which are coming up. I think bifacial has a clear roadmap as being the next generation module technology, both in terms of LCOE as well as module cost-wise.
Right. Thank you. Thank you so much. Dr. Kaushik, a last question. We have paucity of time now, and our attendees have been very patient with us. So the last question which comes across to you is, do you see any issues with the handling of mechanical load as modules become larger?
Yes, certainly. Actually, that should be a concern from module makers as well as asset owners when they are buying larger modules. So I kind of hinted a little bit at this. As modules become larger, obviously their weights go up. And if you think about how the modules are put on, whether it's in a portrait format or landscape format on the racks, with high wind speeds areas and with areas where there's snow loads, mechanical load handling definitely becomes an issue. In this respect, proper framing, as well as we really believe that this is another area where the glass transparent backsheet modules will be an advantage, because if you think about it, in the glass transparent backsheet modules, the glass in the front is a 3.2 mm glass, on the other, which is a tempered glass. On the other hand, with the thinner 2 mm by 2 mm glass modules, it's only a semi-tempered or heat-strengthened glass that is being used in order to reduce the weight. And as the modules become larger, the impact resistance and mechanical load handling capacity of these semi-tempered and heat-strengthened glass definitely are not as high as the 3.2 mm glass. So yes, we believe that as modules become larger, mechanical loads, there's a very high chance, not only in transportation and handling, but also in field operation, can become issues, and module racking technologies will have to, match up to that. And we believe that with the thinner glass, with even thinner glass coming, I think that can be a bigger issue than the clear transparent backsheet based modules.
Amit, let me add something to what,
yes, please.
Yeah, Amit, let me add something to this. What Kaushik said just now, absolutely valid points. So what's happening is the module sizes are increasing because customers are demanding higher power. But at the same time, what is also happening is the wafer size also is increasing. So we are talking about M6 and M12 next generation large wafers. So obviously, as the wafer size increases, the 500-watt module of a few competitors that we have, they are actually using M12 wafers. And those wafers are then make the module size larger. But beyond a certain area, like currently what I guess is 2.4 to 2.5 square meter area, there is hardly any scope for increasing it further. So larger than 2.4, 2.5 square meter modules are going to be much more difficult to handle on the field. And that's why people are shifting from half cut to 1/3 cut wafers in 500 watt peak modules, higher wattage modules. So they are cutting the M12 wafer into 3 pieces to make 3 different solar cells and then stringing them together into the module. One of the other big reason for anything more than 2.5 square meter, for example, is when these modules are installed, especially in fixed mount structures on high windy fields, on ground mount projects, there's a huge amount of uplift force that comes, when the wind goes behind at the back of the module, or it tries to lift up the module. So with the help of the wind force being exacted from the rear side, that can lead to significant stability issues on the structures or on the fixed tilt mounting systems. And it actually leads to higher investment in making the structures or the piling deeper and stronger. So all in all, besides handling, besides the power that we are looking at right now, wind force and structural stability of module sizes in excess of 2.4 to 2.5 square meter is going to be difficult to handle going forward.
Thank you so much. Thank you so much, Mr. Saha. As I said, there's little paucity on time. So all the questions which we could not have answered today would be shared with our panelists, and they would be answered in due course of time. I would also like to take the opportunity of thanking Mr. Ivan Saha and Dr. Kaushik for the informative presentations. I would also take the opportunity of thanking all attendees who joined us from 41 countries from across the globe, and who were part of this webinar. We've had a lot of questions which have come from across the globe, and we would be sharing with our panelists the same thing. On the same note, I would also like to invite each and every one of you at REI E-Expo on 9th of June, for which you will have more details on our website, Renewable Energy India Expo website. And thank you very much for being part of this program for this webinar. And a small little survey would be popping up on your screen right away, and I would request you to please take part of that survey. Thank you so much. This is Amit Sharma signing off from now. Thank you, Mr. Saha. Thank you, Dr. Kaushik. And thank you all our attendees.